This is a tutorial on how to start your cloud native journey. This is the third video of the series here. The first video, we containerize an application. That was the first step in our cloud native journey is containerization. We use Docker and Docker tools to create our containerized application, and we created a container image. The second video was container registry, where we where we first installed a container registry, and we used Harbor, which is a CNCF graduated project. We installed Harbor. We also installed a few prereqs as well. Since that installation of Harbor we used Docker Compose, so we installed Docker Compose. And after that, we had Harbor up and running. We push our container image that we created, and we also pulled our container image from that Harbor instance as well. So the next stop for our cloud native journey is container orchestration or orchestration. Also container runtime as well. Even our first step, we did install Docker. For this step here, we will use Containerd, which is a CNCF graduated project. And Kubernetes, of course, is a CNCF graduated project. So we'll do a few requirements first. First thing, make sure you are in the Kubernetes virtual machine instance here. So click on the Kubernetes tab. First, we'll do some requirements. As of Kubernetes 1.28, that was released in August of 2023. Kubernetes can leverage cgroups v2 for enhanced resource management like swap. Before, if you were to install Kubernetes before, you had to turn swap off. So you had to do a sudo swap off -a. And you also had to disable it in /etc/fstat. So first we'll check to see if our virtual machine is using cgroups v2. And with stats-fc and this command here, it looks like that's great, we are using cgroups v2, so let's proceed. Next, we also need to make sure that IPv4 traffic is forwarded and also let iptableC bridge traffic. So we're going to load several kernel modules as well. So we'll load the overlay module and also the BR netfilter kernel module as well to this environment. And we're going to set them up to load on boot. So we'll make sure we'll add these kernel modules to the right configuration file. Next, we're going to use the modprobe command to add the kernel modules. So we're going to use modprobe to add the overlay and BR netfilter kernel modules. Next, we're going to use modprobe to also add the BR netfilter module. Next, we will make sure that sysctl parameters is persistent just in case if there's any reboots. So we'll make sure that netbridge bridge nfcall iptables equals 1, netbridge bridge nfcall ip6 tables equals 1, and net ipv4 ip4 equals 1 as well. And we're going to reload and we're going to apply these sysctl parameters with sudo sysctl -s system. All right, next we're going to verify that our kernel modules are loaded. So first let's verify that the BR netfilter module is loaded. Next we'll verify that the overlay kernel module is loaded. Next we'll also verify that the netbridge nfcall ip tables, netbridge bridge nfcall ip6 tables, and net ipv4 ip4 system variables are set to 1, even though I did do that before. All right, that's all great. A few more steps as well. We need to install several packages. First package is socat to help redirect traffic within the Kubernetes cluster. So we're going to install socat, this time using a package manager. So as this is installing, we're also going to install contract next. And contract helps connection information between pods and services. We haven't really talked about pods and services. They are Kubernetes resources. Pod is the smallest unit of a Kubernetes resource. I'm going to install this as I talk. And pods could be one or more containers. Pods also live and die. They're mortal, so we could scale up pods as well in case we need more of our instances of our container running. So we need a way to abstract from these pods, and we do that with services. So services abstract away from pods. Service provides us a DNS entry and also a virtual IP as well. And also there's several types of services that will also create load balancers, cloud load balancers as well. There are services that can expose your application outside the Kubernetes cluster, of course. So we could do that with the service type load balancer, most commonly used with cloud load balancers as well. But there is a project there are several projects for bare metal. And also, you could also expose the pod on a high range of ports using what's called a node port type of service. So once that's done, that's already finished here, we'll go to the next step here. So now we will install containerd. And Kubernetes will use containerd to run the containers or orchestrate the containers. So we need a container runtime. So there's a few caveats. We do need a container runtime that is compliant to the container runtime interface of Kubernetes. So Kubernetes uses a container runtime interface, or also called CRI, to interface with the container runtime. So the container runtime that we're going to use also needs to be OCI compliant, of course. So containerd is OCI compliant and CRI compliant, and containerd is a CNCF graduated project, which was donated by Docker. And Docker under the hood is also running containerd and runc. So we're going to need to install containerd from the archive on GitHub. We're going to verify its checksum, and we're going to extract it to /user/local. So the stuff we get, we downloaded the archive from GitHub. Next, we're going to download the SHA-256 checksum, and then we're going to verify the checksum. We're good. Next, we're going to extract the containerd archive to /user/local. Next, we will download a containerd service unit file or systemd unit file for containerd. And we're going to reload. And we're going to enable containerd. Next, we'll download runc, and we'll download runc. Next, we'll verify runc, our archive as well. Download the ASC file. Next, we'll also install runc. There is a verification on the runc ASC file, but that's also on a browser site, so I'll add that link here later. So let's install runc. So there's one more step we need to do. Containerd has a configuration file called config.toml. This config.toml is located in /etc/containerd. So let's make sure we will create that directory. Next, we will use containerd's config command to generate a default config.toml, and we'll make a simple change. So pretty much the only change we need to do on this config.toml is we need to set up the systemd cgroup driver with runc. So we're going to set the systemd cgroup setting to true using sed. Next, we will restart containerd. Let's go to the next step here. A few more prereqs before we can install Kubernetes. We will install the CNI plugin to implement the Kubernetes network model. So we'll set several variables here, and we will install the CNI plugins. Let's download the CNI plugins. Next prereq is CryCTL, or CRI-CTL. CryCTL is a command line tool for a CRI-compatible container runtime, so you can use CryCTL to interact with containerd or other CRI-compliant container runtimes that you use, like CRYO. CryCTL is required for kubeadm, and kubeadm is the installer tool that we're going to use. It's from upstream Kubernetes as well. And we'll use kubeadm in the next few steps. So CryCTL is required for kubeadm and for kubelet, and kubelet is a node agent for Kubernetes. So let's set a few variables here to set the download directory. We're going to make the download directory. We're going to install CryCTL 1.28.0. Our architecture is AMD64. Also, we will now download the archive for CryCTL and also extract it. We will also, now let's test CryCTL version. There's various commands as well, similar to the Docker commands that we use in the first step. So if you go to CryCTL-help, you could take a look to see if you, typo here, CryCTL, see various commands as well. So similar to the Docker commands, there are similar ones. So you could do CryCTL PS as well, logs, etc. Next, we will install kubeadm, kubelet, the kubelet systemd service unit file as well. So let's first check the latest version of Kubernetes. It's 1.28.3. So we will download the appropriate versions of kubeadm, kubelet, and the kubelet systemd service as well. Next, we will download the several archives for kubeadm and kubelet. Next, we will make kubeadm kubelet executable. Next, we will download the kubelet systemd unit file. All right, now let's make the let's run this command. All right, next up, so kubeadm has a configuration file called 10-kubeadm.conf. It's a configuration file on how systemd should run the kubelet. So we will download the 10-kubeadm file. Next, we will enable and start kubelet. Kubelet at this time is going to be crash looping. It's waiting for kubeadm. So last prereq is to install kubecontrol or kubectl or kubectl. It's the Kubernetes CLI tool that used to run commands against Kubernetes clusters. So let's download get the archive for kubectl. We're going to validate the checksum file, download it, then we'll verify. Next, we're going to install kubectl and do a check, kubectl version -- client. The next step here, we're going to try to retrieve our cluster state. So we do expect this to fail because we haven't installed a cluster yet with kubectl cluster -info. Of course, that failed. That's expected. So next, we're going to create a cluster with kubeadm. So we're going to use kubeadm init to initialize a cluster. We're going to use the -s cry -socket to point it to container D, to the container d.sock. We're going to do a dry run first to make sure we're not going to fail any pre-flight checks. You don't necessarily need the -s cri -socket option unless you're using multiple container runtimes. But for posterity, but I do want to use it just to point it out. All right, so that dry run was successful. Now let's actually run it without the dry run option. A few things I want to point out, they might have seen as well. Some options here. Notice this kubeadm join command. And this kubeadm join command will expire in 24 hours, and it is the kubeadm command with the necessary token if you want to add a node to this Kubernetes cluster. You can always generate a new token as well once this expires. So if you want to join any other worker nodes to this Kubernetes cluster, we could use this kubeadm join command. with these tokens. All right, after kubeadm has finished, we do need to make our kubeconfig file we have to place it to where it is expected at, or where kubectl expects that kubeconfig file, and also where Helm expects that kubeconfig file. So it's pretty much a default location. So we will make that first directory .cube, then we will copy that kubeconfig file over, change ownership. Now let's run kubectl cluster info. Now this should be successful. So now we do get that the Kubernetes control plane is running, where it's running, where CoreDNS is running as well. Let's take a look to see first a few things as well. Let's remove a taint on this node. We're running a single node cluster, and it's a control plane node. By default, Kubernetes places a taint on this worker on this node so that you don't have workload scheduled to this node. Because you want control plane nodes to only run the control plane components. But in our case for this tutorial, we will have only a single node cluster. So let's remove the taint. So let's see if if our cluster is ready. So it says not ready yet. So there's one more step before we need a ready Kubernetes cluster. That step is to install a CNI plugin. So we're going to install Cilium, and Cilium will implement the Kubernetes network model. Cilium itself is a CNCF graduated project as well. So let's install Cilium. Now we'll install Cilium 1.14.2. And now let's validate the installation. So this will take a few minutes here. So as this is as we're validating, just to go over the Kubernetes network model, there's several requirements for CNI plugins to implement the Kubernetes network model. Like that pods could talk to other pods, and also pods could talk to other pods and other nodes as well. There's several more as well since this is finished, so let's continue on. We'll test the cluster's readiness, then now it is ready. Now let's take a look to see the other components of Kubernetes. So Kubernetes has its components in the kubesystem namespace. So the command to get pods is kubectl get pods, and you have to supply a namespace. If you don't supply a namespace, it will use the default namespace. So we're going to do kubectl get pods -n and kube-system for its namespace. As you see here, there's several other pods and control plane components of Kubernetes. If you want to point out a few, one is etcd. etcd is a CNCF graduated project. It's a key value store that Kubernetes uses to store all the cluster data. Two more pods here, as we see here, called CoreDNS here. CoreDNS is also a CNCF graduated project, and CoreDNS is a DNS server that trains plugins. For this purpose, CoreDNS serves as a cluster's DNS. All right, so the next step here, we're going to go over Kubernetes basics. Let's create a namespace for our Kubernetes resources that we will create. So we're going to create a namespace by using kubectl to interact with our Kubernetes cluster. We'll do kubecontrol or kubectl create namespace. We'll call the namespace my-namespace. And within this namespace, we're going to create our resources in the next steps. So we'll create a pod, and a pod is the smallest deployable unit in Kubernetes. A pod could be one or more containers. If there are more than one container, typically those containers are working together, or one container might be serving, let's say, might be a login agent, or it might be serving as a proxy. So we're going to first use an imperative command to deploy an Nginx web server. So we're going to use kubectl run. We're going to give it the pod name Nginx, and we're going to use the container image with --image Nginx in the tag 1.25.3. we're going to expose port 80 on that container, and that will be in the my-namespace. We're going to use the -n option for that. So we have pod nginx has been created. Let's go find the pod. We'll do kubectl get pods. We're going to do a -o wide as well to get the virtual IP for this pod, and this will be in the -n my namespace. So we see there's a virtual IP here, or IP for this pod is 10.0.33. Your virtual IP might be different here. So a pod will have a virtual IP assigned to it, and all containers within that pod will have the same virtual IP as well. So if there's multiple containers in the pod, they will have the same virtual IP. So let's run a command. We're going to curl this virtual IP to check to see if our nginx web server is running. This is not click to run because everyone's virtual IP can and will be different. So you have to type in copy and paste. That is from the harbor section. Let's do. And let's just get the first 4 lines. All right, so our web server is running. For now, we're going to, this web server is not actually accessible to the outside the cluster. So we'll take a look on how we do that. So let's delete this pod for now. So we're going to create several resources, one type of resource to scale this application, and another resource to expose this nginx web server to outside the Kubernetes cluster. So the first resource we're going to create is called a deployment. And a deployment, it provides a way that Kubernetes could do updates at a controlled rate for our application for these pods. This time, for this purpose or this step, we will create what's called a Kubernetes manifest. And for Kubernetes manifest is the most common way to actually launch and create Kubernetes resources. We're going to create a deployment manifest, as we see here. Just to go over, there's 4 required fields in a manifest API version, the kind metadata. We have to give it a name and a namespace as well. If the namespace is not included, then it'll be the default namespace. Then you have that spec of that type of resource. So this is a deployment spec. A deployment it also manages a number of the identical replicas of the same pod. So within a deployment spec, there is what we call a pod template. And with the pod template, it will give the pods the same label, app equals nginx. And this deployment will control, using this label selector, all pods with the label app equals nginx and within the same namespace. Now within this pod template, we have the pod spec now. So this pod spec, we will run a single container. Under containers, if we were to have multiple containers in this pod, there will be another entry here. We will call this container nginx, and we'll use the container image nginx 1.25.3, and it will expose the container port 80. So we created that manifest. Now we'll do kubectl apply to apply the configuration from this deployment manifest in deployment.yaml. So we'll do kubectl apply -f to point to the file. There's also kubectl create. There's a difference between create and apply. With kubectl apply, if the resource has been created, it will update that resource. With kubectl create, if that resource is already running, it would error out and fail. So most folks will use kubectl apply. So now our deployment is running. So let's go check out our deployment to make sure it's up and running. So yep, we have our deployment, nginx with 2 pods, 2 are available. So now let's take a look at the virtual IPs of the pods with kubectl get pods -n my namespace -o wide. So we have our pods running with 2 virtual IPs with their own virtual IP. So we need a way to abstract this group of pods over a network. So we're going to use a resource type called a service. So a service will use a label selector as well to identify the pods to expose. So similar to the deployment, services will also use a label selector to abstract the pods with the appropriate label. So we will also use a node port type of service. A node port type of service will expose the service on each node's IP of the cluster, and by default, it will expose that application on the port range of 30,000 to 32,767. First step here, we will create a manifest for the service with this click to run. Note its API version and client and metadata and the service spec. Notice in the service spec we have given a type node port and the label selector app equals nginx. This was the labels that we ran for that we had for the pod as well. And for this case, we are exposing the container port. We'll map the node port 30,000 on the node's IP to the container port of 80. So let's do kubectl apply again to apply this manifest to create the service. So now the service has been created. Let's take a look to see where that service, let's see if that service is created with kubectl get service and this my namespace. So service is up and running as well. Let's take a look at with the browser, see if we can access our nginx web server, and we see it's available. All right, let's go to the next step here. So I'm going to pause this video for now. We've installed Kubernetes, we installed the requirements for Kubernetes and the containerd runtime, and we also saw that Kubernetes also use two other CNCF graduated projects, etcd and core DNS as well.